Hello everyone, my name is Prashant and this is the part third of the series of lecture. Uh, the part one is the file system and second one is the process management. This is the third part which is called a memory, Linux memory architecture, in which I am talking about the like a virtual and physical memory and all the difference and all the tuning parameters which we can utilize. So memory management is one of the most important thing which the Linux kernel does because like I mentioned in my previous video, like a process is one of the most important thing which kernel does because it's a user space application and running the user space application is one of the most important thing that the kernel does. So whenever this process is running, it need a memory, and to allocate this memory, kernel do that work really smartly. So in case of a Linux, this memory management is like dynamic in nature. So and this because it's like it's depend upon your load requirement and everything. So means what are the current tasks which are currently executing. So because these number of processes which are running in your system is changes rapidly, so kernel need to handle like this memory management really efficiently and really well. So before we are going to discuss about like different parameters which we can tune to improve the performance of our existing system, let's discuss something about your physical versus a virtual memory. And before that, like let's discuss about a 32-bit versus 64-bit system. So in the present modern days, we have a choice between a 32-bit system versus a 64-bit system. So one of the major stuff like why mostly the people or the company are going for a 64-bit system because a 32-bit system has some limitation. For example, in a case of a 32-bit system, because sorry, the 32-bit system has some limitation because in a case of a 32-bit system, the split between a user space and a kernel space is like 3 is to 1. So your 3 GB is for user space and 1 GB is for kernel space. And in the case of a 64-bit system, there is no such limitation. So uh, let's look at here. So basically what kernel does is to divide your entire memory into different zones, and the reason kernel divides this memory area into different zones because it's a because of the hardware limitation. So let's say your ISA devices, which are used majorly for your keyboards and everything, can only access the first 16 MB of memory, which is called a DMA or direct memory access. So because of these hardware limitation, kernel divides memory into different zones like DMA, normal zones, and high mem in case of a 32-bit. In case of a 64-bit is like DMA, DMA32, and normal zone. So the reason the kernel split all these, first is hardware limitation, and second one is it's want to group the similar pages together or similar properties together. So this is zone DMA. While in case of a 64-bit system like DMA you have, then you have a DMA32 like a for example this ISA devices which can only 16 MB. There are some 32-bit devices, but the major difference between your 32-bit system and 64-bit system that in case of a memory pressure, the kernel can use this DMA32 region. While in your normal zone in case of a 64-bit contain both your user space process as well as kernel space process. So this ends up whatever the limitation which is provided by a 32-bit. So like here, your DMA is less than 16 MB, then 16 MB to 896 is where your kernel data structure reside, and greater than 896 MB is your user space process reside. And this is one of the major limitation with 32-bit system because your process can maximum access up to a 4 GB. So if there is a kind of a memory pressure, you will and it try to access the area beyond that limit, you will see all kind of issues like a or out of memory killer. So this is something about a memory management unit. So means we have a 32-bit operating system and a 64 we have and like we have discussed about 32-bit system and 64-bit memory operating system. So let's discuss something about your virtual memory and physical memory. So your this physical memory architecture or what we call your physical memory or RAM is generally been hidden to your application as well as a user. And whenever the user demand any kind of a memory, so OS maps this memory, this any amount of memory to a virtual memory. So when an application requests a memory, kernel gives him a map of a virtual memory. So generally, then to map this virtual memory to physical memory, we have a hardware device which is called MMU or a memory management unit, which is generally been the part of your CPU, but it can be a separate dedicated chip. So this memory management unit take care of mapping this your virtual memory to physical memory. So this is how the entire Linux virtual memory manager looks. So here you can see, and on the extreme left hand side, like Bash and HTTPD and Mozilla, these are your user space application. And then you have a glibc, which is a uh, means you can glibc, and then you have a kernel subsystem. So to interact with your kernel, you need to make a system call, which has been provided by your glibc interface. Then you have a slab allocator where the kernel memory is assigned, zone body allocator, which is responsible for making your memory area contiguous. Then, like I already described, memory management unit, which is used to map your physical memory to your virtual memory, so that everything being hidden from your user application side or from the user perspective. Then we have a kswapd. In case of a memory pressure, in case of a memory pressure, then this is a daemon which runs. Generally, it is been on the sleeping state, and it is try to reclaim the your pages. Then we have BD flush, or nowadays we have a PD flush or per BDI flush, which is responsible for flushing out your dirty pages, and ultimately your data being returned to your disk. Uh, being returned to your disk. So let's discuss something about your buddy system. So means kernel maintains uh, the free pages with the help of something called a buddy list or a buddy system. So one of the most important tasks it does is to maintain the free pages as well as to make the memory area contiguous. And this will help to prevent any kind of a memory fragmentation, because if the pages is scattered, it is really difficult to allocate a large portion of pages. So what buddy system does is to maintain a free pages and tries to allocate pages for page allocation request. So in your system, let's look at the demo point of view. You have something called proc buddy info, which hold out per zone wise free pages or this much. So you will see, and if you're not able to figure out, like this is the number of 4 KB pages which are free, 8 KB pages, 16 KB pages, your 32 KB pages, and all. You can run this command echo m proc sysrq hyphen trigger, and then go to your var log messages to see out the number of pages which are free. For example, for DMA32 you have 509 4 KB pages available. You have 2026 8 KB available, free pages available. So pretty much the system is doing nothing. That's why you see these many amount of number of free pages available for the system, for the application. One of the most important thing you need to look out is that this all unreclaimable parameter, which is set to, which is no. So in case of a memory pressure, or in case you see a out of memory killer condition, you see that all the kernel has nothing to reclaim from them particular zone. And then because your threshold is reached and kernel is not able to reclaim any pages, so generally your number of free bits, number of free pages, which is a watermark set for the particular zone, will fall below this minimum limit, and generally you see the out of memory killer condition. Next thing is page frame reclamation, which we already discussed, like kswapd. kswapd is a thread which generally been you can see in the sleeping state. So see, you generally see this thread is running on the sleeping state, and it whenever the threshold is reached and the kernel want to reclaim pages, this is the thread which is responsible for doing this, and it will call a function called try to free page, and responsible for your page reclamation. So like I said, whenever the limit falls below the particular limit in a particular zone, and then this daemon will wakes up, and it uses an algorithm called LRU, or a least recently used algorithm, to find it out, like these are the pages which are least recently used and should be released first to free up the memory or to release the memory pressure. Now look at the swapping, which is like a one of the most talked concept, or which is one of the most misleading concept. So generally most of the people look at the output of this command and see, like there are some amount of pages which are occupied in the swap, and they will like freak out that your system is not working properly, or there is some kind of memory issue, which is a kind of a misleading. It will happen or it doesn't be an issue. So for example, uh, let me run one application, exe g, we have memory, we have test. I'll explain it what I'm trying to do, and this much. So let's look at the output of this, and you will see that some amount of memory is being swapped. Okay, so the most easiest ways to find out if your system is really thrashed with that swapping issue is just to run this command, pmstat 1, and let's say for 10. Then there is a parameter called swap in and swap out, where you can see if your system is actually doing the swapping or not. Okay, there are other way, for example star with hyphen w 1 and 10. So here you have a page swap in and page swap out if your system is actually doing the swap in. So means kernel memory manager is really smart enough to deal with these kind of situations. So for example, if your system during startup, if there are some daemons which are lost, which are launched and is hardly going to use anymore, kernel means move those pages into a swap to save out your expensive memory. So one of the major issue which people see is, for example, let's say you have a memory pressure and the kernel move those pages to your swap, and now let's say after a few hours or a few means after a few hours that memory pressure is released, and let's say that process doesn't exist anymore. So kernel will never try to move that pages back to your RAM, and that pages will reside in your swap forever. So generally all those monitoring tools will like continuously bugging you that there is some amount of a data in your swap. So actually that process doesn't exist anymore, so you don't need to worry about it. But if after running this VM chat or SAR command you see that your system is continuously doing swap in and swap out activity, then you need to worry. Then you need an extra RAM or you need to tune your application. So how kernel will decide like which page to be cached, or which page either it need to reclaim a page from a page cache, or it need to move the page to the swap in a case of a memory pressure. So it uses an algorithm called swap tendency. So let's say I start a process which requires some amount of memory. Now it asks kernel to allocate some amount of memory. Now kernel has a two choices: either to drop a page from a page cache, or it move the existing page to the swap. So kernel uses an algorithm called swap underscore tendency. So if the output of uh, that that algorithm comes out to be greater than 100, then that page is eligible to be swapped. If that output is come to be less than 100, then we can reclaim a page from your page cache. This is how it can do. So it will means it swap underscore tendency is equal to how this algorithm is equal to map ratio uh, plus distress value and VM underscore swappiness. So what is the map ratio? So it is a mapping between your virtual to physical memory. So whenever you run this command proc mem info, you see some of the pages which are mapped. So for example, for this system we have 56 MB of pages roughly which are mapped. Okay, distress value is like, for example, how much trouble is kernel in freeing up that particular memory, and then we have a parameter called swappiness, which is generally default value set to 60. Here it is 80. So I change it for some testing purpose, so I can revert it back to 60. So okay, so means for our application like database where the swapping is like really a performance issue, that it recommend to change this value to even lower down to 60, so that when you lower down this value to not to 60, not to 10, then if the kernel need to calculate based on your swap underscore tendency, then kernel will means try to keep a page from the page cache instead of means drop a page from the page cache instead to moving it to your swap area. So let's look at few more things. Let me take out one more session. And run this command watch and okay, and let me try to allocate some amount of physical memory. Okay, so if you see, your swap area has already been shoot up. Okay, so how to find out like which process, like here I run this process, so I know this is a culprit process, but how exactly you can find out in case of a real life situation? So for that, in the GitHub we have some of the script through which you can easily find out like which process is responsible for swapping. So here, if you run the script called swaputilization.sh, you will see. So here you will see that memtest is one of the process. For example, it's like roughly 137,420 amount of swap which is being utilized by this process. So in this way you can easily find it out, like what is the culprit process. Okay, one other script which I want to share with you guys. For example, most of the people have their own inbuilt script or own customized script, and what they do is like resident memory is your RAM and this is your virtual memory. So when they sum up all your resident memory, and at the end when they come out up to the conclusion, when they sum it up all these things, they find out that the sum of this all resident memory is comes out greater to your actual RAM. So how then this be possible, like the sum of this resident memories comes out to be greater than your actual RAM? And the reason for that, for example, when you run the top command, you have this virtual memory, resident memory, or something called a shared memory. That is the pages which is being shared between your system. So yesterday I show you the output of this command, and we have this shared library where I told you that this read only is the one which is being shared between the processes. Okay, so for that purpose I have downloaded one more script from this GitHub which will tell you the actual memory utilization per process. So when you run this script, this is actually a Python script. So it will tell you, it's fast. This will tell you the actual amount of memory this process is using, the amount of shared memory, and the sum of these. So in this way you can find it out like what is the actual memory which is being used by this process, the amount of shared pages, and it will give you the sum at the end. That this is the total amount of memory which is being used by this process. Okay, so in this way there is no confusion like what are the shared pages and what are the actual pages which is being used by this process. So before summing it out, let's talk about some of the tuning parameters. So first one we have already discussed about the swappiness parameter. So generally it is set to 60 in most of the operating system, but for the application like database, it has been recommended to lower down to 10 or even to 0. But one thing to remember is that you cannot stop kernel to swap out the pages, because this is how the kernel will design. In case of memory pressure, or in case if kernel thinks that these are the pages or the bunch of anonymous pages which is being can be moved to the swap to make a room for the existing pages, then kernel will certainly move those pages to your swap area. Now let's look at the second parameter called VM dirty background ratio here, which has been default set to a value of 10. So what is this VM dirty background ratio? So VM dirty background ratio is the percentage of the total available memory. This is total available memory, not the total memory. Means it is the sum of your free pages plus your reclaimable pages at which your flusher daemon, which is like a PD flush or BDI flush daemon, writes your data to a disk. Okay? Means these daemon will responsible, means whenever the total amount of dirty pages will reach to this value, the kernel will automatically flush means that this PD flush or per BDI flush will automatically flush those pages to your RAM. Similar to dirty background ratio, we have something called dirty ratio. The only difference between that, in this case, the application which is generating a dirty pages itself, whenever this limit is hit, the kernel, the application itself start writing those dirty pages to disk. Okay. And except for that, we have two more parameter: dirty write back centisecond. So dirty write back centisecond is like you have this flusher thread which are being periodically wakes up and write your data to a disk. So this like when this means when this a flusher thread will wakes up and to flush the data from your RAM to disk. So this tuner will define the interval, and if you want to disable it, you can set it to 0. Then we have something called VM dirty expire centisecond, which is comes out to be the hundredth of a second. Like centisecond is like, for example, this is 5 seconds. When your data is old enough to be pushed to the disk. So means kernel thread need to be decided like whenever the data reached or hit to this value, the flusher thread will automatically flush the data to the disk. So this is all about memory management, a little bit introduction to management in memory management, and some tunables. So thanks for watching this video. In case of any question, you can write it to me to laprashant@gmail.com. Thanks once again.